So this is example on the what we call per phase analysis for three-phase system. This is extracted from example 2.7 from Saadat book on power system analysis. So the problem is you're given three-phase line, a three-phase system having a line impedance of 2.J4 ohms as shown in this figure. So the line feeds to balanced three-phase load. So we have to see the highlight. The keywords of this problem, right? It's feeding the two balanced three-phase load connected in parallel. The first load, so the two loads are given in terms of impedance. The first load is the Y connected. So the Y connection is here. Basically, this is the first load. Okay, this is the load number one, first load connected in Y, having the equal impedance of 30 plus J 40 ohm per phase. So by saying this is a balanced three-phase system, so meaning that the loads for each of these three phases are equal. Okay, this is the 30 plus J 40 ohm. So similarly, this is also 30 plus J 40 ohms, right? So that's this one. So that's why this is balanced, right? The second load is delta connected. So the delta is over here. Okay, this is the second load having the impedance of 30 minus J 40 ohms. So you can notice from here that the load which has positive reactive part or positive imaginary part, okay, can you still recall that because the XL, the reactance of the inductance, right, or we call inductive reactance is omega L. Okay, it's omega L, and XC is negative 1 over omega C, because when you shouldn't get confused with the C, right? When we say C is equal to R plus JX, so the X here is just imaginary part of the complex number. So the complex number here, it's called impedance. Okay, impedance. And when we say the just imaginary part of which this is called reactance. Okay, and the R here is resistance. So all of these three quantities are having the units of ohms. So they share the same units, right? So the line is energized at the setting end from three-phase balance system, three-phase balance supply of line voltage. So the problem says that the line is energized. Okay, line is energized means that this is a supply by the source voltage. Okay, with the V line of the magnitude of 207.85 volts. So the voltage at this point. Okay, the voltage at the setting end is given. Okay, taking the phase voltage VA as a reference, so you determine the current real power, reactive power drawn from the supply. So the problem asks you to determine the current drawing from the supply side. Okay, so you should be able to find this I from the supply side or from the sending end, right? This is the total current that is drawn from the source. Okay, so having known this, the current drawing from the supply, and you know the voltage at the supply, so you should be able to find the complex power delivered by the source or by the supply, right? So that's why the problem in the problem A also asks you to find the real and reactive power drawn from the supply. So in this case, you see. All right, the problem gives you the VL at this sending end. So knowing this VL, okay, VL standing from line to line voltage. So you should think of the formula of S three phase, because it is a three phase system. Okay, this is S3 phase, which is equal to square root 3 times, okay, this is a root 3 times V, right, V line to line times I line, right? Or we should write V line, I line conjugate. So we are talking about the power, the three-phase power at the supply side. So the VL here, V line to line here is at the supply side. So this is already given. So you need to determine the I drawn from the supply, the total current drawn from the supply. So knowing this IS, you should be able to find the complex power, three-phase complex power, right, delivered by the source. So you just decompose the real part and imaginary part, so you can answer the question A. All right. For the question B, the line voltage at the combined load. So meaning that the problem asks you to determine the voltage at the receiving end. Okay, this is at the receiving end voltage. Okay. So from this picture, right, probably you know it's at the receiving end voltage is here. Okay, this is at the V receiving. So the problem B asks you to determine the V at the receiving end. Okay, and the question C asks you to determine the current per phase in each load. So meaning that we have to determine the voltage at each load. Okay, meaning here for one load. Okay, the load is represented as this because the load is given in terms of the impedance. So you need to find the current flowing into each of these load. All right, this is the question number 3. Okay, we have to determine the I here. Okay, flowing in each load. So question D asks you to find the total and real power in each load and the line. So basically you can see from here problem asks you to compute the complex power. Okay, because the problem says real and reactive power, meaning here you have to determine the complex power of each load. Okay, complex power or S for each load. Okay, and the real and reactive power of the line. So now you also have to compute S of the line. Okay, now you can see from here the problem D and from the problem A, D and A. Okay, because the problem A asks you to find the complex power drawn from the source, right? So you can see that from the law of energy conservation. Okay, law of the energy conservation. You see that the energy produced by the source has to be the same as the total sum of the energy flowing to the load and plus the losses, right? So now you can say that due to the energy conservation, okay, the S at the supply side must be equal to the sum of the S at the load. In this case, this is S1 and S2 because this is S1, the load 1, right? This is the complex power consumed by the load, and this is the S2. S2 is the complex power consumption by the load 2. Okay, now you see, and this is the complex power consumed by the line, right? So the SS is complex power supplied by the source at this case. Okay, so the mathematical representation of the energy conservation would be in this case. Okay, in this case the conservation would be S at the source has to be equal to S1 plus S2 plus S loss. Okay, S line, sorry, it is to be S line because we use the term S line. Okay, complex power of the line. So soon after you compute the problem D, the sum of all the quantities that you determine from problem D has to be exactly the same, or mostly, right? It has to be very close to the real, the complex sum of real and reactive power drawn by the source. Okay. Now let's. Why don't you just pause this video and try to solve this problem? Try to use the knowledge you learned from the lecture to solve this problem yourself, and then we will come back for the solution. Okay. Let's see. Okay, we will do the solution for this problem. So the thing is, when we trying to determine when trying to solve the this kind of problem, all right, what you have to do is that you should write the three-phase. Okay, you should trying to come up with the per-phase representation. Okay, the three-phase representation can be written in this way. Okay. Now you see this is the diagram again, and then you can write the per phase. Okay. Remember that the per phase representation, you need to have the all the loads connected into Y connection. Okay, and then you know that if it is a balanced three-phase, then there is no neutral current. Okay, the concept is that you have to, if you have the delta, okay, if delta load exists, okay, right, you have to convert it to Y connection. Okay, because we need to have the neutral. Okay, and then because the I neutral is 0 in balanced three-phase system. Okay, because we need to have this property. Okay, now you can see that you have one delta load here. Okay, you need to convert this into to the delta to the star connection or Y connection. Now you can see that for the Y connection you need to have the neutral point like this. Okay, then when you convert this, okay, it would look like this one. This is the after the connection, right? So this is a neutral, the new neutral point, neutral. All right. So and then what you can do is that the neutral, there is no current flowing through the neutral. Okay. So if you redraw this picture in one phase, so let's take the phase A as an example, because the problem says that you need to compute the voltage with respect to the phase A. So I draw the phase A here, and this is the source of the phase A, and this is the impedance of the line. 2 plus j 4 ohms, and now you see this is the point here. Okay, this is a point X over here. This is X. So the X, you have the 30 plus j 40 ohms connected to the neutral. So it is like this. Okay, this is neutral, and here you have 30, and this is j 40. Okay, so soon after the conversion, right? This is the point A or X. Should be A. This is not A because this should be A prime, right? Let's denote this because this is the point A, B, C. It is not A anymore because the voltage the voltage at these 2 points is not the same. Okay. Because there is a voltage drop when there is a current flowing through this, there is a voltage drop across the line. So the A point, these 2 points are never be the same. So let's denote this point as A prime, B prime, and C prime. Okay, the point here, since this is the same node as this one, so this is also the point A prime. This is point A prime on the picture, right? So this is the for load 2. Okay, you need to, after the conversion, this is the new impedance connected to the neutral. Okay, connected at the point A prime as well. Okay, so now it is your duty to recall how to have the delta y conversion. All right, the delta y conversion is pretty straightforward. Okay, if you have something like this, okay, this is called delta load, and if you want to if you want to convert this into y connection, okay, y connection would be you would need to have the neutral point, okay, and the neutral point is in between here. This is the phase A, B, and C. For example, this is the neutral point. Okay, for example, here this is C1, C2, C3. Okay, what is the Z here? For example, this is CA. So the CA here, it is the multiplication between Z1 and Z2. Okay, oh sorry, it should be C1, C2, C3, and CA, and divided by the sum C1 plus C2 plus Z3. Okay, so the ZA is in between these two Z1 and Z2 in the delta connection. So when the transformation, you have to get the product of these two impedance in which the Y impedance is in between. Okay, similarly, if you want to find the ZB here, the ZB here is what? ZB is in between Z1 and Z3, so this is C1, C3 divided by the total sum, so this is C1 plus C2 plus Z3, right? Okay, similarly you can write the formula for CC on your own, okay? But if it is a balance, delta connection, so the Z1, Z2 and Z3 are the same. Okay, if it is balanced, then Z1 is equal to Z2 is equal to Z3, which is C here, right? It is Z, okay, to a certain constant Z, all right? So you can see from here that C1 times C2, C1, C2, here it is C1, C2 is Z square, okay? This is divided by what? Divided by the sum of C1 plus C2 plus C3. This is 3 times C, right? Okay, this is 3 times of C. Now you can see that the Z just cancel for 1, so it is C divided by 3. So in summary, if it is a balanced delta connection and you want to transform to the delta to the star connection, okay, the impedance will be reduced by 3 times. Okay, for this case, okay, you want to convert this 60 minus J45 so into the star connection. Okay, the impedance in star connection becomes 3 times less than the delta connection. So this is 20 minus J 15 ohms. Okay, 20 minus J 15. Now what you have to do here is that you just analyze the circuit from here. Okay, this is the problem also gives you the voltage at the supply side, which is here. Okay, but remember the problem says that the voltage at the supply side is VL, which is 207.85 volts. So when we write in terms of phase quantity, because you see this is phase A with respect to the neutral, the voltage here must be reduced by square root 3 times, right? So you have to get 207.85 divided by root 3. Okay, since the voltage here is given, right? So when we compute other quantities from this circuit, you have to put the reference at this point, right? Because there is no point to refer in the circuit. You just refer to the you just give the reference to the known voltage quantity. all right, and the other phase angle will be with respect to this this voltage here at this point. Okay, now it is clear, hopefully, right? So 207.85, if you use your calculator, that would get, you would get 120 and angle of 0, and the voltage here is in volts, right? And the problem asks you, the problem A asks you to compute the currents from the supply side, right? So let's denote this current from the supply side as an IS here from the supply side. Now you can see that you know the voltage, right? You know the all the impedances here, so you can compute the IS here. So the way that you solve this, okay, it's very straightforward. This is from your circuit class. Okay, you need to find the total impedance over here, and you apply the voltage at this point with the equivalent impedance, and you could find the IS. So let's determine this CEQ, the total equivalent impedance. Okay, so the CEQ here, it is this guy 2 plus J4 in parallel with, in series with these two in parallel. So this means that this is 30 minus J40 in parallel with 20 minus J15. All right, that is easy, okay, because here, okay, that would becomes two impedance in parallel. The total impedance would be the multiplication of these two, okay, multiplication of these two divided by the sum. The sum would be 50 minus, right, this is 50 minus J 55, right, and this one you should get 22 minus J4. Let's check the result yourself, right? In this case, you can see that this is minus J4 and this is plus J4. So your CEQ will have just real part, okay, 24 ohms. Okay, the CEQ becomes just 24 ohms. So soon after you have 24 ohms, you can say that the IS, okay, IS is equal to Vs divided by CEQ, right? And hope this is not too fast. If you find this is hard for you to understand, okay, this is not the problem with power system. All right, this is a problem of your circuit class, so you have to revise it seriously with your in your circuit lecture, right? In this case, this is 120 and angle of 0 divided by 24. So in this case, 120 divided by 24, you should get 5 and angle of 0, because there is no, in this case this is a reference and there is no reactive part for the CEQ as well. So you get the total current supply by the source, it is 5 amp. Okay. Now let's compute the because the problem A asks you to find the real and reactive power drawn from the supply. Okay, so the problem A asks you to also to compute the S as the source. So S as the source would be your Vs times Is conjugate, right? Since this is per phase, okay, this is per phase. When you want to compute this in 3 phase, you have to multiply this by 3 because this is balance, right? The load is the computation is just in per 1 phase. Okay, this is the circuit from 1 phase. So if you want to answer this, it is not just the quantity you compute from this circuit, because this is in 1 phase. Okay, remember this is just 1 phase because we use per phase analysis. So when you answer this question, as answering the question, you have to get back to the three-phase quantity, because the system here is in three-phase, right? The system is in three-phase. So you have to multiply this by 3. You shouldn't get confused with this. Why? How this 3 comes from? Okay, where this 3 comes from? Because the quantity that you get, Vs and Is, are in one phase, but your system has 3 phase, balanced 3 phase. So that's why you can multiply this by 3. All right. So you can find that this is 3 and 120 angle of 0 multiplied by 5 angle of 0, and actually this is the conjugate. So negative of 0 is 0. Okay. Now you get what? This is what you get, 1800. Okay. Angle of 0. That means that you don't get the reactive power. Okay, in rectangular or Cartesian coordinate, this is 1800 plus J0. What's the unit of this? So remember, in this lecture, in this subject, it's just very important that you have to write the unit. All right, you have to write the unit all the way, otherwise you will get confused. Okay, this is in volt, this is in amp, so the multiplication of these two and the unit of S is this VA. Okay, meaning that the complex power supplied by the source is 1800 VA, or you could say that this is 1800 watt or 1.8 kilowatt. Okay. You just have the active part. Okay, this is question A. We answered the question A. For the question B, the problems ask you to determine the voltage at the combined load. So let's see at the equivalent circuit of this. Okay, the equivalent circuit of this problem is that you see the calculation from here, you will see, this is the diagram. Okay, and what is it here? This is reactance, right? The line voltage at the combined load. The two loads are here. In this case, this is the load, the two loads, combined loads, right? The problem says that what is the line voltage at the combined load? So if you compute this voltage at this position, all right, what is the voltage here? You can see that you know the Is and you know the voltage at this at the source, right? And that creates the current flowing through the line, which is equal to, in this case, 5 amps flowing into this one. Now you can see that you can compute the voltage drop across this impedance, right? So the voltage at this point is essentially the voltage difference between voltage at the source and the voltage drop on the line. Okay. Now you could answer the second question. Okay. I didn't compute this in my solution yet, but you should do it yourself. Okay. You could do it yourself. In this case, what you can see is that you have to compute V at the V load here. Okay, let's do this. I will just give the method, right? And I ask you to check the numbers yourself. Okay, so your VL here is what? It is 120 and angle of 0 minus 5 angle of 0. This is I times Z, which is 2 plus J4. Right, let's do it quickly, because this is 120 minus 5 times, this is 5 times 2, this is becomes 10, right? 5 times J4, this is J20, right? J20. Now that would becomes 110 minus J20. So you, as I said earlier, right, you have to convert this into the polar form. Let's do this yourself. Okay, this is in both. All right, and this is for one phase. if you want to see all right, it's the same as because you can see in this case the voltage drop, or this is the voltage drop at the load, right? When you have to when you need to answer this is the you have to answer, to give the answer in what, in the line to line quantity. Okay, so in this case you have to give it as root 3 times the V line that you computed, V load that you computed earlier, right, from this guy here. Okay, 120 minus J20, right, 110 minus J20. Okay, and then this is the answer, right? And you have to put the angle difference, the phase angle shift by 30 degree. Okay, and you put the e to the j 30 degree. Okay, this is e to the j 30. It means the same as this guy here. Okay, so I just leave this to you. You can also check with the example 2.7 in Saadat. Okay, whether you get the same results or not. All right, and let's go straight to question number 3 or question C here. It asks you to find the current per phase in each load. The current per phase, this is here, this is phase quantity, right? This is the per phase or single phase circuit. Okay, so the problem asks you to find the current per phase. That means that the problem wants to see, because the problem wants to see this current, the current flowing into each phase. This is I1 and this is I2. Okay, so the problem C, okay, asks you to give the answer for I1 and I2. Now this is becoming the circuit again. This, what do we call, how do we call this kind of circuit? You know the total current flowing. Okay, this is 5 amp flowing into this node A, and there are two paths that can divide this or can separate the IS of 5 amp into two paths, right? This is called the current divider, right? If you put into the circuit that you learn, okay, probably it would look like this. This is the what we call current divider. Okay, current divider. This is IS, this is C1 or R1. You can say this is R1 if it is an R1 and R2 for the DC circuit, right? How would you find the I1 here and I2 here? Okay, your I1, it is what? It is R2 divided by R1 plus R2 times IS, right? And I2, okay, the I2 is R1 minus R1 plus R2 times IS. Okay, just remember this way. If you want to find the current division of the resistor R1, right? This is a ratio of the opposite resistor, which is R2 divided by the sum of these two. So now you can see that if you sum I1 plus I2, it must be equal to IS. So you see from the right side that this is a ratio, right? These two coefficients are the ratio. So when you sum I1 plus I2, the sum of these two guys becomes 1, right? Now let's go back to our circuit here. If you want to see I1, if you want to get the I1 should be what is the value here? This is the 20 minus J15, right? So the I1 is the current flowing into this guy. So you have to get the ratio between the opposite, right? Impedance, which is 20 minus J15 divided by the sum of these two. The sum of these two would be what is the sum of these two? This is 50, right? 50 and minus j 25, correct? This is mine. Oh, sorry, this is plus j 25. Okay, plus j 25. And you have to multiply this by the total current, because this is the ratio of the total current, which is 5 and angle of 0. I just omit this, the phase component. Okay, that should be your answer. Okay, I will give this answer to you in Cartesian coordinate. This is 1 minus j2, and you know that if you do the calculation, right, the sum of I1 and I2 must be 5. So your I2 would be, right, what is the I2? I2 is the current flowing into 20 minus j15. So the ratio would be j30 plus j40 divided by the same guy here, 50 plus j25 times 5. So in this case you get 4 plus j2m. So notice that the sum of these two is 5, right? The sum of these two is 5. Correct? Right. This is the things that we have computed already. Okay. This is also the answer, because the problem asks you for problem C. Okay. Problem C, it's the current flowing into each phase. So this is the phase, the current flowing into each of the phase. Okay, flowing into the phase. Now let's compute the problem D, question D. Question D asks you to find the total real and reactive power in each load and the line. So as I said earlier, we need to see the S1, S2, right? Remember, S1 must be in three-phase quantity, okay? And S2, S1, S2, and S3 must be in three-phase quantity, and the sum of the three powers must be exactly the same as SS. In this case, the SS has been computed already. Okay, that is 1800 VA, just active component. Okay, so we have to compute these three quantities, and we have to make sure that the sum of all these three must be 1800, right? So let's do the calculation. So you know it already that the voltage drop across the load is 110 minus j20, right? So the load, this is at the load, right, like this. I redraw this, 30 minus plus j40, this is the load one, and 20 minus j15 ohms. And you know that the voltage drop at this at the combined load, or that it at the load premises, is what? Is 110, right? 110 minus j20 volts. Okay. Now with these two quantities, you can find the complex power delivered to the first load, and the complex power being consumed by the second load. Okay. Let's denote the power of this first load as S1. Complex power of the load here at S2, right? So remember, when I write the underscore here means the complex quantity, right? So when you have the S1, your S1 is what? S1, it is a voltage drop, right? That is V1, V, okay, this is V times I conjugate. Now your I here you have already computed. Okay, the I was I1, right? What was I1? The quantity of I1 was 1 minus j2, and the I2, okay, the I2 you have already computed, which is 4 plus j2, right? That's why the sum of I1 plus I2, which is equal to 5m, right? So there are two ways that you can compute the S1 like this. You can use the basic definition of the complex power, which is V1 V times I conjugate. All right, I will do both. All right, this is for the first time I will do both. V times I conjugate. I conjugate would be 1 plus J2. Okay, remember this is an I conjugate. Okay, and since you have the three phase, okay, you multiply this by 3 because this is the total power delivered to the load. Okay, because this is the balanced three phase, you have to put 3. All right, so this is the value that you should get. All right, this is the value that you should get, which is when multiplied by 3 you get 450 plus J 600 VA. Okay, multiplied by 3. Alternatively, you could also find from in this way. Okay, you know that S is equal to V times I conjugate, right? Okay, if you know just the voltage drop across this, because these two are connected in parallel, so you just know, if you know just V and you know Z, okay, what you can find the complex, how would you find the complex power? Okay, V and Z, you just have to transform the I to V and Z, so you know that the V I is V divided by Z, okay, from Ohm's laws, and this is conjugate. All right, so this would become V times V conjugate becomes V square. Remember, V square here just the magnitude of the phasor divided by Z conjugate. Okay, this is the formula. Okay, make sure that you get this one. Okay, or if you know just I and Z, okay, that would be equal to, if you know I and Z, you just change the V. So V is equal to I times Z, okay, and I conjugate is here, right? I times I conjugate, that becomes I square. That's just a magnitude, right? This is the I square, because you remember, if you get 3 plus J2 multiplied by the conjugate of this guy, or it could be 3 minus J2, right? 3 minus J2, then what you get is the square of this magnitude of this guy, right? There is no imaginary part of this. Okay, I square times Z. Okay, so in summary, when you need to compute the complex power, okay, the square term V times Z, because all these are in complex. When you just remember this way, when you have the V square, right? V squared, if your V is complex, then it would become just a magnitude, okay? V squared, but wherever you have the C here, this is becomes the C conjugate, right? Okay, if it is S is equal to V squared divided by the C conjugate, S is equal to I squared times Z, okay? And if you are talking about three phase, balanced three phase, then you have to multiply all the way through by 3, right? Okay, so the key explanation here would lie with this two formula. Okay, this is S in 3 phase, of course, 3 phase. Okay, in 3 phase. Now you can do the same in the same way. Okay, now you get S2. Okay, let's do in this way. You can get from 3 times, but this is the square of this guy. I didn't put it, so you have to. I will leave this for your own calculation, right? But I will just put the this method. Okay. The V is 110 minus J20, and the I conjugate, the I2 would be, what's an I2? I2 is 4 plus J2 and the conjugate of which is 4 minus J2. Okay, 4 minus J2. Okay, that you should get 1200 minus 900. Oh, sorry, this is 900. The unit of which is VA, right? And S of the line. Now, the current flowing through the line is, remember, if the flowing through the line is 5 amps. So this is the impedance here. Impedance, what was an impedance? 2 plus J4. The current flowing with the amplitude of 5 amp flowing through this impedance here, right? So now you can use this formula, 3 times I squared C. So 3 times I squared, which is 5 square times C, that is what? 2 plus J4, right? 25 times 25, this would becomes 25 times 3, 75, right? Times 2 plus J4. Okay, these two, 25 times 2, this is 150, right? Plus 150, this is J 300 VA. Okay, now you have everything, right? You have everything that you would need for this for this answer. Now let us check the results. We check the results. Okay, this is important step when you learn engineering, right? You should be able to justify, or at least to check the result yourself, whether the computed one is corrected or not, right? Is correct or not. Okay, this is the key achievement when you learn something, right? You should be in the position that you can say this is right, this is wrong by yourself. Okay, now you see your S1, the sum of S1 plus S2 plus S line. What is it? Okay, S1 plus S2 plus S line. So this is the line. This is S1, this is S2, and this is S line. The 3 circles on the screen. All right. Now you can see the sum of these 3. Okay. 450 plus 150 is what? It is 600. 600 plus 1200. This is 1800. Okay. Now this is get 1800. Okay. Then you get imaginary part, 600 plus 300 becomes 900, plus 900 minus 900. This is become 0. So the sum of this is 1800 VA, which is exactly the same as S source. So that concludes the calculation that all the answers are correct. All right, and then also, this comes to the end of this example. I hope you will find this useful for your study. Thank you for listening.